Hello, my name is Jack Willett, and this is my final project report for the optimization of visiting the national parks in the contiguous U.S. The problem that I analyzed in my project was to find optimal or near optimal routes to visit the national parks in the contiguous U.S. And in that, there were two cases. Case one trip to visit all the national parks, and case two, multiple trips to visit smaller subsets of the parks. The constraints that I added on top of the ones that are required to make the MATLAB scripts work were that all trips must start and end in St. Louis, and only those with visitor centers in the contiguous US were considered, which cut the list of 63 total parks down to 50 parks. Then specific to case two, each trip must visit at least 3 parks and last between 5 and 22 days, assuming traveling at 55 miles per hour on average and spending 24 hours at each park. And then specific to case two, again, there's a secondary goal to identify trips, if any, that may form a basis for a statewide tourism campaign. The method I used to solve both cases was the traveling salesman problem. In a classic traveling salesman problem, given a list of cities and distances between them, find the optimal route by minimizing the distance for one salesman to visit each city, starting and ending at the same point. This is the method I used to solve case one. In case two, I used a variant of this called the multiple traveling salesman problem, where a list of cities is split between multiple salesmen. While there is a wide variety of methods that can be used to solve a TSP, the method I used to solve case one was integer linear programming, and the method for case two was a genetic algorithm. Both methods here provide a heuristic solution, meaning that while you might not obtain the optimum solution, you will obtain a near optimum solution at a much reduced computation time. And here again, both methods provide a discrete search space. For case one, with one salesman visiting 50 parks, this is based off MATLAB's traveling salesman problem example script, which uses integer linear programming. The results from this case are a distance of 11,508 miles and a total travel time of just under 59 days. The solution was obtained in just over 1 second with an absolute gap of 0, indicating an optimal solution. Here's the map with the route. And here's the order that the parks will be visited in. So for case two, with n salesmen each visiting a subset of the parks, the solution is based off a script from the MathWorks file exchange, which uses a genetic algorithm, and I set it to run 10,000 generations. And this script runs in a loop that adds one salesman in each iteration of the loop until the time constraints are met. This provides a relatively volatile solution, where you rarely obtain the same or even similar solutions from run to run. However, I counted this as a positive because if you don't like the solution you get in one run, you can run again and get a completely different solution. So because of this, what's presented here is just an example of the output. And in this case, I got 7 salesmen or 7 unique trips with distances ranging from just over 2,000 miles to just over 5,000 miles, and travel times ranging from about 7 days to about 19 days. And this solution was obtained in just under 3 minutes, and that includes all the time to loop up to 7 trips. Here is the map with the 7 unique routes and the best of generation plot in the lower right. And here's the order that the parks will be visited in each of the 7 trips. So some potential future work would be to integrate real-world map and road data and speed limits to improve the time and distance calculations. Next would be to implement a weighting scheme to allow more or less time at each park, where parks you want to spend more time at are weighted higher and vice versa. And while no obvious single statewide tourist trips were discovered in the example case 2 solution, this script can still be used or adapted to plan other trips where you know you won't be wasting time by taking a non-optimal route. Thank you very much.